In this video, we're going to be taking a look at the diffraction grating simulation, and we're going to be seeing how wavelength, slit width, and slit spacing affect the angle of diffraction. So the first thing that we're going to take a look at is the wavelength. So the wavelength right now is set to 550 nanometers, and we're going to take a look at region 1, or n equals 1, the first peak to the right of the central bright spot. Let's just take a look and fit the graph to our screen, and we're going to zoom in, and hopefully this is going to work. Yeah, we're going to zoom in here. We go to the top of that peak up there, and we look down here, and that value is a theta value of about 0.14 or so. So let's try to remember that value or write it down. We'll go back and we'll fit the graph to screen. Now we're going to change the wavelength, and we're going to increase the wavelength, and I'm going to go to the extreme for this simulation and go up to 700. So we're going to max it out, and again we're going to fit the graph to our screen, and we're going to zoom in on that n equals 1 area. So if I do that, I'm going to zoom in, and I look for the top of that peak. It's right around there. Come down, and we're at around 0.185. So write that number down. We see that as the wavelength increases, the value of theta increases as well. So we have more diffraction. So let's take a look at the influence on slit width. So we're going to fit that back to screen. I'm going to put my wavelength back at 550 nanometers. And if we take a look again, what we're going to do is zoom in on n equals 1. This is the same as the other region, but just to do it again, we're going to get a theta value about 0.14, but let's do it anyways because that's what the instructions for the simulation say. So I'm going to take my pointer, and I'm going to zoom in again, and there's that theta value, and we're at 0.14 or 0.1455 or so. That's the area of the peak. Let's see what the influence is when we increase the slit width to 0.2. So right now it's at 0.1 millimeters. Let's crank it up and go to 0.2. So the slit width now is maxed out at 0.2. Let's try to find that first peak to the right of center, and I'm going to zoom in on that. So let's see if that's going to work. Yeah, there we go. Zoom in, and there's the peak right there. If I go down, I'm looking at a 0.112, a value of theta right around there. So we can see that as the slit width got bigger, our theta value decreased. It was at 0.14. It's down to 0.11. So as slit width increases, diffraction decreases. The value of theta goes down. Let's do it again. Okay, so now we're going to take a look at slit spacing. We've reset our thing, and we're going to put this back down to 0.1 so that we're setting at where we started at. Again, let's take a look at that first peak, and oh, surprise, surprise, we're back at 0.14. So that hasn't changed. We'll fit that back in there, and let's take a look at and see what happens if we increase the slit spacing and we max that value out, and we can max it out to 0.5. So we're going to increase the slit spacing to 0.5. Now we've got a bunch of little peaks. We got to find n equals 1. Again, I'm going to try to zoom in on that area in the simulation and do an estimation. And there's my peak right here. I'm looking down, and it's at around 0.06. So it was at 0.14 before. It's decreased to 0.06. So we can state that as the slit width increases, our value of theta gets smaller, and therefore we have less diffraction. So I hope that simulation helps you understand the concept, and you might just have to commit those to memory, especially for the slit spacing, because that's not available within the formula. So I hope that helps.